Hello, Vananda. This is Ramesh, lecturer in civil engineering, Government Polytechnic, Station Bangalore. The course is reinforced concrete structures. And lecture 4, we are going to discuss the design of T beams by limit state method as per IS 456 2000. After completion of this lecture, you are able to know how to determine the depth of nickel axis in T beams and how to determine the moment of resistance of the uh, T beams, because here the moment of resistance of the T beams is dependent upon the position of the neutral axis. Right? So we will discuss how to determine the depth of neutral axis and how to based on that how to determine the moment of resistance as per IS 456 2000. Before going to start today's lecture, just I would like to recap whatever we were discussed in our last lecture. In last lecture, we were discussed about the what is mean by T and where it can be used, where the beams are designed as a T beams or L beams, because where uh, the beam and slabs are constructed are cast monolithic. So in that cases, you can design as a T beam or L beam. And later we will discuss about what are the different component parts of the T section and how to determine the uh, uh, effective width of the flange and the actual width of the flange, and what is the difference between actual width of the flange and the effective width of it. And as per IS 456 we have discussed the effective width of the flange for homogeneous sections as well as for isolated TB and LB. And then we were discussed about what is mean by maximum reinforcement and minimum reinforcement, and how to determine and how to compare this maximum reinforcement and minimum reinforcement. And similarly, we have discussed about the conditions of maximum and minimum reinforcement, because the required reinforcement or the provided tension reinforcement should not be greater than the maximum reinforcement uh, given by IS 456 2000. Similarly, it should not be less than the minimum reinforcement proposed by the IS 456 2000. So, therefore, the condition is the provided or required reinforcement should be greater than the minimum reinforcement and less than the maximum reinforcement. Right. So, at last, we were discussed about what are the advantages of beam as compared to rectangular beams or normal beams. So, these are the things we were discussed in our last class, right? Then, just these are the dimensions of the T beam. It means so here uh, this is the width of the flange and this is the df is the depth of the flange or thickness of the slab, and this is the bed, and this will call it as effective depth of the T beam. That means the distance from the extreme compression fiber to the center of the tension reinforcement. We will call it as effective depth of the beam. Then this is overall depth of the beam, and this is BW is the width of the flange. This is width of the T. These are the dimensions of the T. So what is mean by neutral axis? This is the definition is same as whatever we discussed in singly reinforced beam. That means the neutral axis means it is a axis which is passes through the member where the stresses are zero. It means across the section of a member along which the stresses is zero. That means at the neutral axis the stresses are zero, right? And above and below neutral axis is divided as a compression zone or tension zone, right? If it is a simply supported beam, the tension zone is on bottom fiber and compression zone is on top fibers. If it is a cantilever beam, the compression fiber is on bottom side and tension fibers is on top side, right? And the depth of neutral axis can be determined by the so this neutral axis can be determined by equating the compression force to tension force. That means if you observe this, uh, at the neutral axis, uh, the stresses are zero, right? So therefore, it can be determined by equating the compression force equal to tension force. We will discuss how to determine all this. Then, then if once we calculated the neutral axis, then we can determine the moment of resistance of the member, right? Because I'm not going to discuss about the details of this neutral axis because all these things we were covered in our design of rectangular beam. So the moment of resistance and T beam is depends upon the depth of neutral axis. Because if the depth of neutral axis changes, then the moment of resistance will also change. So, the difference between the rectangular beam and these T beams are because this is a rectangular beam, right? And this is a neutral axis, right? And here the width of the beam is same at bottom and top, or at least up to the uh, depth of neutral axis it is same. So therefore, if you observe these stress zones, and this is the stress zone is up to some portion in rectangle, then it is varying to the parabolic shape. So throughout the depth of neutral axis, the stress zone is the stress distribution, and below that the stress is constant at the reinforcement because we are assuming that the total tensile force is taken by the steel only, right? So, but in T beam, what happens? So this is a T beam, right? So if this is the stress block, for example, if I take this is the stress block, due to the stress, the variation of the stress block is also same, but only the difference is the distribution of stress block is depends upon the depth of neutral axis, whether it is within the flange or the web, right? So that you need to determine before going to determine the depth of neutral axis as well as to determine the moment of resistance. This is very, very important, and this is the difference between the rectangular beams and T beams because based upon the uh, location of the neutral axis, the bending moment equation will change, right? Because here the width is not uniform. Up to the this level, the width of the beam is different, and after that, the width of the beam is different. So that is why it is very important to determine the location of the neutral axis, whether it is within the flange or within the web, before going to design the TV, right? So then we will discuss how to determine that whether it is within the flange or in the web. So based upon that, there are two cases. Case one is neutral axis within the flange, right? And second case is the neutral axis lies within the web. Just now I told you, no? So this is a TB, right? And this is the TB. So if the depth of neutral axis is within the plant, that means here, or up to here, or within the web is up to here. So how can you define or how can you classify these two? If the depth of neutral axis is within the plant means uh, df, df is uh, greater than x, I can say like, right, or xu is less than df. So if df is greater than xu, then we can classify that it is case 1, that means the neutral axis is within the plant. So if the df is greater than xu, that means the thickness of the plant is greater than the depth of neutral axis, that means the neutral axis is within the plant. If the uh, depth of plant df is less than the xu, right? That means the df is less than the xu, the thickness of plant less than the depth of neutral axis, then that means the neutral axis is within the pen. So there are two different methods. If the neutral axis is within the plant, the moment of resistance calculation is different than the if the neutral axis is within the pen. Right. Again, the if the neutral axis is within the web, it is further classified into two types. That is, if df by d is less than zero point 0.2 and if the df by d is greater than 0.2. It is nothing but, so it is depends upon the stress diagram, because if the is as we discussed in our singly reinforced beam, the df, the distribution of compressive stress is the combination of a rectangle up to here and parabola. If the df by d is less than or equal to 0.2, that means throughout this rectangle portion, the stress is constant. So it is very easy to determine for this case, right? And suppose if it is df by d is greater than zero point 0.2, then what happens? The rectangular and parabola case. So I would like to just zoom the this is let us say this is the plan, and if you draw this stress distribution diagram for this case, so it will be like, right? So within this, actually the rectangular portion is the distance is 3/7 of x cube, right? That is 3/7 of x cube, this value, the rectangular portion. If this is the case, then it is very difficult to determine the average stress, because some portion is under parabolic case, some portion is under rectangle. If it is if the rectangular portion exactly, if it is in exactly the rectangular portion, then it is easy to calculate the compressive force of this rectangular force separator and parabolic, right? So if this is the case, how to determine the moment of resistance, and if this is the case, then how to determine the moment of resistance. So these things we will discuss now, right? So this is the three cases based upon the depth of neutral. So come to the case one. That means if the depth of neutral axis is within the plant, that means the rectangular portion is restricted to within this. If you observe this diagram, see this rectangle, total stress distribution is within the plant, right? So you can easily determine this is as similar to the rectangular beam, right? So similar to the rectangular beam. Because why? Because above the neutral axis it is compressive zone, below neutral axis is tension zone. So in tension zone the only stress is due to the reinforcement. So here we will not consider all this area because in tension zone we are assuming that the total tension force is taken by the steel itself. There is no contribution to the concrete. In compression zone, as usually the width is not changing, so it is similar to the rectangular beam of width TF. The width of the beam is TF or PF, which is PF, effective width of the flange. And as usual, the overall depth is D, small d, this one, right? So, what is the if it is within the flange, then how to determine the actual neutral axis? That the neutral axis should be determined by equating the compressive force equal to tension force, right? So here the compressive force is CU 0.36 FCK into BF into XT, where B of F is equal to effective width of the flange, right? FCK is the strength of the concrete and XT is the actual depth of the neutral axis. And the tension force is TU is equal to 0.87 F of y into AS, where F of y is the yield strength of the steel and A of ST is the area of tension reinforcement, right? And the neutral lever arm is nothing but the distance between the compressive force to tension force, that is D minus 0.42 X, right? So XU should be calculated by equating the compressive force equal to tension force, that is 0.36 FCK into BF into XU is equal to 0.87 F of y into AS, right? So that means XU is equal to same as your XU becomes how much 0.87 F of y into A of ST by 0.87 A of by 0.36 FCK into here we need to write B of yeah, right? B of S, that is the effective width of the flange. So from this you can calculate the actual depth of neutral. So then after the moment of resistance is depends upon the depth of neutral axis. So now we have calculated the first case, if the neutral axis is within the flange, then you can calculate the XU by equating compressive force to tension force. So after that, then again you need to determine the XU max, that is the limiting depth of neutral axis. As per codal provision, it is based upon the grade of steel. You need to determine the XU max, that is already given in your code. So, as per codal provision, XU max by T, that is the limiting depth of neutral axis from class number 39.1. You can open and see 39.1. This. Yeah. So as per the codal provision, the XU max equal to for XU max by D is for 250 grade steel, XU max is 0.53 XU max by D value, and 415 value is 0.48 XU max by D value, and similarly for 500 the XU max by D value is 0.4. So by using these values you can determine the XU max, that is limiting depth of neutral axis. Then you can determine, classify the section based upon the actual depth of neutral axis and XU max. If XU is equal to XU max, right, then it is called as balanced section. If XU is less than XU max, then we call it as under reinforced section. And if XU is greater than XU max, then we call it as over reinforced section. This is similar to our rectangular beam, right? So if the based upon the XU and XU max, you just classify the type of the beam. And as I told that in our previous classes, as per I guess 2000, we should avoid the over reinforced section. If you got XU is greater than XU max, you should restrict your XU to XU max, right? Because due to the provision of over reinforced section, the failure occurs in concrete. Therefore, it is a sudden failure. So, as per IS 450,000, we cannot, we should avoid the sudden failures, right? So, then if X is greater than X max, then restrict your actual depth of neutral axis equal to the limiting depth of neutral axis. Then you can find out the moment of resistance. So, if it is a balanced section, the moment of resistance is uh, whether it is compressive force into lever arm or tension force into lever arm. You can calculate any one of these. It is a balanced section. If it is an under reinforced section, under reinforced, that means the failure occurs in tension zone, right? Therefore, the moment of resistance is equal to 0.87 f of y into AST into T minus 0.42 x. And if it is a over reinforced section, therefore the XU should be limited to XU max. Therefore, the compressive force into lever arm. So here the XU becomes XU max, right? That is 0.36 FTK into BF into XU into T minus 0.42 XU. So here XU becomes XU max. This is a over reinforced. So like this, you can determine the moment of resistance of a T section if the depth of neutral axis is within the flange, right? Now coming to the second case, that is if the depth of neutral axis is within the web, then how to determine the moment of resistance? And before that, just see the parameters. Just now I told you the BF is the effective width of the flange. F of CK is the characteristic compressive strength of concrete. F of Y is the yield strength of steel. And XU is the depth of neutral axis. B is the effective depth and BW is the width of the web. Now coming to the second case, if the neutral axis within the web, that means XU is greater than DF, right? Just now I have shown if XU is greater than DF, there are two cases will rise. That is, if the rectangular portion is within the flange, thickness of flange, or it is exceeds the flange. That means if this is the flange, this is the web. So if you draw the stress distribution diagram, if this case is occurred, that means the rectangular portion is restricted to within the line. This is the neutral. That means up to this level, it is rectangular portion. Maybe some extended it may happen because the rectangular portion is within this. And suppose let us say, for example, I would like to write it as, yeah, this is here, and here the stress is 0.45 FCK, right? And here also you will get same. So for this portion you can consider as average stress. For this portion it is a constant if this is the case, right? So this is different case. That means if the stress distribution block is, the stress within this is not uniform. That means this way I would like to write that diagram. If this is the flange and this is the bed, and if you observe the stress distribution diagram, up to here it is rectangle, then it is parabola. That means within rectangular there are two types. Up to here it is a rectangle, and so here the portion of rectangle up to here rectangle, and this is parabola. So if this is the case, it's very difficult to determine the average stress, right? So in this case, how to determine the moment of rest? So these two things we will discuss now. First, consider a case of first case, if the depth of neutral axis is within the web and df by d is less than 0.2, that means the stress distribution within the flange is rectangle, right? So just keep in mind. Then how to determine the moment of rest, right? So as usual, if calculate the compressive force, the section is divided into two parts. If this is the case, as I told now, just as I showed. See, so it is clear that you can easily observe here. Up to here, the depth of the it is a rectangular portion uniform. After that, it is a parabola. So for you can calculate the compressive force for this case separate and this case separate, right? You see, first of all, you need to calculate the compressive force as the tension force. If you are able to calculate the compressive force and tension force, then it is very easy to determine the neutral axis, depth of neutral axis. And if you know the depth of neutral axis, then you can easily determine the moment of resistance. So here, so for analyzing this case, that means if df by d is less than or equal to 0.2, that means the stress within the flange is rectangular distribution. So in this case, I can just divide it into two parts. That means the compressive force taken by the, I can divide the section like this, right? Because see, here in this case the stress is uniform, but here it is a parabolic distribution, and it is a 10.45 FCK here, right? And it is a parabolic distribution. So I can calculate the compressive force taken by the flange, these two portion, and I can take the compressive force taken by this third portion, right? So how to calculate the compressive force taken by these two flanges is nothing but what uh, the average stress is same because this is 0.45 FCK into BF minus BW. That means this portion you will get the distance from here to here and here to here. So BF minus BW into DF. You will get the compressive force taken by these two flanges, right? Then the compressive force taken by this web can be calculated. So this is the stress distribution block for this rectangular portion. So I can take it as average stress, that is 0.36 FCK into dW into X. Is it clear? This is very, very important in this T beams to understand the concept. Okay, right? So if you are able to understand this one, it is very easy to design the T beams just for the design purpose. So if this is the case, that means the stress within the flange or thickness of flange is uniform, constant, I can say, right? That is point. The rectangular portion is within the flange. So for calculation of compressive force, in this case, it can be divided into two parts. That that is the compressive force taken by the flanges and force taken by the web. So for this, the width of the flange is Bf minus Bw. So I will remain only this thing, right? That is area of this one how much? Bf minus Bw into Bf, you will get the area of this flanges into stress, that is 0.45 FC. And for this case, area of this one is Bw into Xu, thus here up to neutral axis, into average stress, that is 0.36 H. Then you will get the compression. And tensile force is same 0.87 F of phi into AS. Then equate compressive force equal to tension force and determine the Xu, right? So then you can determine the moment of resistance. That means lever arm into force. See, similarly, same way we have divided into here. The first case is only this case. Only the compressive force is taken by the rectangular force, and this is the stress diagram. That is the maximum is 0.4 CFCK, and this is the force, the point of action of force for this case, right? And this is the lever arm is D minus 0.42 X, and this is X. And the force is 0.3 X CU W is nothing but the compressive force taken by the web, and CUF is nothing but the compressive force taken by the flanges. See, here it is divided separately. So this is BF minus BW by 2, BF minus BW by 2. You get the right. The area of this one is BF minus BW to BF, and within this area, the stress is constant, that is 0.445 FC. And the distance from the centroidal distance from compressive force to tension force, in this case it is D minus dF by 2, because it is a rectangular portion, it will act at a distance of D by 2 from here, right? So up to here it is from here to here it is D, so D minus dF by 2 the lever, right? And the moment of resistance, after calculating X value, you can calculate the moment of resistance. That means the compressive force taken by the web into lever arm plus moment due to this one, and plus the compressive force taken by the flange into lever arm, that is D minus AF by 2, right? So like this you have to determine the moment of resistance. So this is the compressive force taken by the leg 0.36 FCK into BW into XU max, XU or XU max, and the compressive force in rectangle of size, that is BF minus BW into DF, that is 0.446 FCK to BF minus BW into DF, and this is the tension. And you just equate all these things and you will get the XU, and you can calculate the moment of resistance. Right? So then moment of depth of neutral axis, compressive force plus compressive force taken by the uh, web and compressive force taken by the flanges. So equate it and you can find out the this is tension force. Equate it and find out the XU. This is not XU max. You need to determine the actual XU, right? Don't substitute XU max. So then the moment of resistance is mu with respect to steel is 0.87 F of by KS into Z, and with respect to concrete is 0.36 FC into B into, here you need to substitute XU, you need to determine T minus 0.42. This is moment due to the web, and this is moment due to the flange. This is here by 2. right? So this formula is already given in a lecture G 2.2. Based upon that, we can calculate the moment of resistance for this case. That means df by d is less than or equal to 0.2. Right? So next case, when when the depth of neutral axis is within the web, but df by d is greater than 0.2. That means the stress within the thickness of flange is the combination of rectangle as well as parabola. So just observe here from this diagram. See, if you take it as this one, so up to the here it is not uniform or it is not constant. It is the combination of parabola as well as rectangle. So in this case, it is very difficult to analyze the or very difficult to determine the compressive forces. So for this one, as per IS 456 2000, if the depth of neutral axis is within the web and df by d is greater than zero point 0.2, then you need to modify the thickness of the flange of the section, right? How to modify the thickness of flange width is already given in your IS 456 2000 in annexure G. If you have, you can open the G 2.2, right? So you just see the limiting value of the movement of resistance of the section may be obtained by the following equation when the df by d ratio exceeds 0.2. So this is for not exceed. Let me just page number 97, 2.2.1. When df by d ratio exceeds 0.2, the moment of resistance of the section may be calculated by the following equation. So in this equation, it is given that yf. What is yf? Yf is the uh, yf is nothing but it is the modified thickness of flange. The modified thickness of flange, right? So that modified thickness of flange is nothing but yf, and that yf should be calculated as per IS 456 2000. So it is already given the formula in IS 2000. You just calculate the modified thickness of flange. That means we are assuming that within this modified thickness of flange, the the stress distribution is rectangle. See here, this is the modified thickness of flange, and within this, the stress is constant, right? So in this case, you just calculate the modified thickness of flange, that is YF, is equal to 0.15 x2 plus 0.65 df, but it should not be greater than df. You need to check with respect to df and calculate this yf, right? Then determine the yf, then equate the compressive point if you know the df and it is exactly similar to the uh, similar to this case. Instead of putting df, you just put it as yf in this equation. That is modified. So that is yf is equal to 0.15 xt plus 0.65 df, and in no case it should not be greater than df. And calculate the actual neutral axis by equating the compressive force equal to tension force, that is 0.36 fck into bw into xu plus 0.45 fck into bf minus bw into yf. This is the modified of flange, right? And here 0.87 f of y into x. But remember, Here, one interesting is this YF is also in terms of X. So therefore, while calculating the XC value, this YF should be substituted in terms of XU directly. So therefore, everything is known in this equation except XU. Then determine the XC value, right? And that XC value should be substituted in this equation for getting YF, right? So that is the actual procedure to determine the uh, depth of neutral axis for the modified thickness YF, right? So after determining the moment of resistance and everything is similar to previous one, that is as I showed that. So this is a calculation of the moment of XU 0.87 F of y into AST minus 0.45 FCK into PF minus VW into YF by 0.36 FCK into VW. And the moment of resistance for this case is we just replace YF in terms of DF. That's it. That's no difference. The modified that is 0.36 K into VW into XU D minus 0.42 XC plus 0.45 FCK into VF into VF minus VW into YF into D minus 0.5 YF. So like this, you need to determine the moment of resistance per part, right? So this is how you need to determine the depth of neutral axis as well as the moment of resistance of the thing. So uh, for this, I would like to conclude the today's class. So just summarizing what we were discussed till now. So today we will discuss about how to determine what is mean by neutral axis, moment of resistance, and how to determine this neutral axis and moment of resistance in T beams. That means in T beam, the moment of resistance is depends upon the depth of neutral axis, right? So because based upon this one, uh, thickness of the flange, it will change the stress distribution diagram. So first two cases, that means if the depth of neutral axis is within the flange, then the calculation of neutral axis and moment of resistance is similar to the rectangular beam, but the width of the beam you need to consider as bigger, right? So except that it is similar to the singly reinforced. That means you need to equate compression force equal to tension force to determine the XU, and based upon the uh, grade of T, you need to determine the uh, limiting depth of neutral, right? So you just compare it and classify the type of section, and according to the type of section, you can use the moment of resistance formula and determine the moment of resistance. That is the case one. That means if the depth of neutral axis is within the flat. Now coming to the depth of neutral axis is within the wave, then the stress distribution is different, right? So in the based upon stress distribution, it is classified into again two types, right? That is, if the df by small d is less than or equal to zero point 0.2, that means the stress within the flange is uniform, right? And if the df by d is greater than zero point 0.2, that means the stress within the thickness of flange is not uniform. Therefore, there are different procedures we need to uh, determine the moment of resistance, right? So, if the depth of df by d is greater than less than zero point 0.2, then uh, you need to divide the sections into two parts. That means the compressive force taken by the flanges separately, and again the compressive force taken by the web separately. and you can calculate the total compressive force, right? And if it is the dF by d value is greater than 0.2, that means the stress is not uniform within the thickness of flat. That means it's a combination of rectangle as well as parabola, right? And it is not joining at the zero also, right? So in this case, what happened? You need to, as per the IS 450,000, you need to modify the thickness of flange to make that the rectangular stress distribution is within with the thickness of the flange, right? So that modified thickness we need to determine, that is called as YT, and YT should be calculated as per the coded provision. Then you can substitute these values and find out the XT value. And based if you know the XT value, then you can find out the moment of resistance. Right. So these are the things we were discussed in today's class. So in next class, we will solve some example problems for better understanding. So thank you.